Good afternoon. We move on from where we stopped in the last class. In the last class, we solved some problem on resolution of forces. Okay, so where we solved forces into x and y components. So we'll move on today. Somebody brought this problem, so I want us to solve it before we consider something else. But this will be the last class or live class for this because the concept we have left is better thoughts when we see face to face. Plus, the lecturer has not even really gotten to this point we are, so there's no need to rush things beyond this point. So we solve this last question, 2.41. Question says determine the required tension in cable AC, knowing that the resultant of the three forces exerted at point C of boom BC must be directed along BC. So that's the diagram it refers to. So it says that you have to determine the required tension in cable AC. So you can see cable AC right there. So points this on the screen. You can see cable AC. This is cable AC being referred to. So we want to find the tension in cable AC. So as we have said in the previous classes, tension should point away from the points under consideration, or should be directed away from the points under consideration. So in this case, try to find out what is the point under consideration. The question says determine the required tension in cable AC, knowing that the resultant of the three forces exerted at point C. So the point of interest is point C. So the particle we are considering is that at point C. That means the the concurrent forces are the concurrent forces, meaning forces acting at the same point. So the concurrent forces we are interested in this case are those forces acting at point C, as you can see this right on the board on the screen. So that means the so-called tension in cable AC that we're interested in is going to be directed away from point C. That means it will be directed along this cable, but away from point C towards the point A. So that is going to be the direction of that tension. Okay, and so, or the force due to the tension. Okay, so we have that force, the tension force, we have this force and this force. So those are the forces acted at point C of the boom. So this is the boom. So the forces exerted on this will be this, and the tension. Alright, so we are told that the resultant of these three forces must be directed along BC. So the resultant of everything must be directed along BC. That means the resultant of everything is along this line. Okay, so we want to use that information to get the value or the magnitude of the tension. Alright, and then we want to get from that the corresponding magnitude of the resultant. So that is the information. So from this diagram, we take the point of interest, the point C, which is the point of interest. Then we show the forces acting on point C, including their orientations. When you refer to forces, you have to be specific about not just their magnitude but also their direction. So we take into consideration their orientation and also their direction, of the direction of their resultants, as we have been told right here. Alright, so that is that about that. So let's solve this. Okay, so we'll pick the points of interest. We first produce an illustrative diagram. So to do that, we'll pick our point of interest. That's the point C in this case, and then we show the forces acting on point C. Being told that we have some 75 pound force. Okay, so this 75 pounds force. So we draw that. We have another one, 50 pound force, which is acting vertically downwards. So we have this 50 pound force acting vertically downward. So we're told that between this and this is angle 25 degrees. So this is 75 pounds, this is 50 pounds. Alright, so at the point C, then we are told that we have the tension. So I have the tension, which is unknown for now. So, and we have it directed this way. So like we already saw, this is going to be directed away from the point C, because the point C is our point of interest, the point in consideration in this case. So we denote that as some unknown T. So this is our point C. Then we are now told that the resultant of all the forces exerted at this point is now before we do that, we should notice the direction of this as indicated in this diagram. Okay, other points are not of interest, so we are doing all of this just for the sake of direction of the forces of interest. So this is 65 degrees right here. Then we are told that the resultant of everything is along CB, so everything is along this line, such that this line is at some angle 35 degrees with the vertical. So we're told this is at 35 degrees with the vertical. Alright, so that is all the information we can extract from that. Of course, this will be some point B. It may not even be point B, it may be any point along BC. Okay, so we know that this is the direction BC. So we're only sure of one thing. We are sure that the resultant of these three forces is along this line. It's along this line BC, and this line is at 35 degrees with the vertical. Okay, so as given in the diagram, the 50 pound force is also vertical, which make this to be alternate angles. So this is also 35 degrees. I mean, this and these are alternate angles. Okay, because this is vertical, this is vertical, this is the same line. Alright, so that is sorted now. So we can decide to resolve the forces along this direction. So the resultant of these three forces being along this direction means that if we get the component of each one of them, if I get the component of this 50 pound force in this direction, get the component of this 75 pound force in this direction, and get the component of this tension force in this direction, and sum all of them, okay, it will give me the resultant. And again, if I decide to find or establish some position which is perpendicular to or some axis which is perpendicular to this BC, then it will happen that on the perpendicular axis, if I get the resultant of all the forces and sum their components along the perpendicular axis, it is going to be 0. Okay, I hope you understand what this means. What we're trying to say is this: if you have, for instance, these are as your usual x and y axis, and it happens that you have some force combinations, you have a force directed this way, you have another one directed this way, okay, such that the resultant at the end of the day points in this direction. If the resultant points in this direction, it means that when you get the component of this force to this direction and the component of this force to this direction, and you sum them, their sum is going to give you exactly that resultant, which is along this direction. If it now happens that you get their vertical components, it will happen that their vertical components, when you add them, is going to become 0, because if it were not 0, their resultant would not have been in this perpendicular direction, So that is the idea here. Because the resultant of this and this is given or is known to be along this direction, then the resultant of their components in the perpendicular direction is 0, because that is the only condition under which their resultant will be directed this way. So we can use that idea to get t, for instance. So how do we do that? We find out what is the component of the force T along a direction perpendicular to this. What is the component of this along a direction perpendicular to this? Along a direction perpendicular to this, that is along this direction. So if we obtain the component of T in this direction, we obtain the component of this in this direction, we obtain the component of this in this direction, then we sum everything. That summation must give us 0. Why? Because the resultant of everything being in this direction means that the resultant component along this direction is 0. This is the perpendicular direction. Alright, so I can say that this is some axis. I can name this axis X. Why am I doing this, or why is this allowed? Because no such X or Y axis was defined in the given problem. Hence, in our analysis, we are at liberty to choose axis for ourselves. Okay, so that's what I'm doing here. So I'm choosing this as Y axis, and I'm choosing this as X axis. Okay, you could, if you were solving this, you could choose this as Y axis and say this is X axis. What is important is that the axes are perpendicular. So that is what is important in this case. These axes are perpendicular, that is, they are at 90 degrees to each other. So having that in mind is what will make this solution correct. If that is not so, then our solution is not correct. Okay, so now having said that, we can now proceed to do the resolution. As a matter of fact, you can as well name this X prime and Y prime, especially if you are given an original diagram that had X and Y notation. So in order not to confuse yourself, you can call this X prime and Y prime. Okay, so with this we are good to go. So then we will now say that now this can be solved in another way anyways, but I hope you understand what I'm doing. That's the most important thing. Okay, so now having done this, you can then say what will be the components of this, okay, each one of them along this axis. So that's what we are going to have to find out now. So we have to find out the different angles each one of them makes with this. Okay, so we are very sure that this is 65 degrees. It was given in the problem. We are sure this is 35 degrees. It was given in the problem. Okay, we are also sure this is 35 degrees because these and these are vertical lines, okay, which means they are parallel lines. So these and these are alternate angles. So again, we can use that to obtain the angle A. So either you add this and subtract their sum from 180 degrees to get this, because this makes a triangle, or these three lines make a triangle. So you can get that from A. Right, so when you do that, you're going to have something like this: 180 minus 65 minus 35. So that's going to give us 80 degrees. 80 degrees. So I have here 80 degrees. Okay, so that is the angle that this force makes with this axis. So it means that if I were to extend this axis that is perpendicular, this one is perpendicular to this one. So if I were to extend this perpendicular, it will go this way, such that this angle, it means now that this new perpendicular, this one is perpendicular to this, such that the angle between this and this T and our Y prime axis is 10 degrees, because this one is meant to be 90 degrees. So that is that. About that, quite clear. Okay, don't get yourself confused. This doesn't appear straight, but it's meant to be a straight axis. I mean, this straight like this, it's meant to be straight, the same line. So this is the same line, Y prime. So okay, so this is the same X prime coming up to this. So this is X prime axis. Okay, so this one is 10 degrees. That's the angle it makes with this. So we can see this one makes this 50-pound force makes angle of 35 degrees with this x prime axis. Okay, so if you want to get its resultant to this side, it will be quite easy to do. You already know the angle it makes with this axis. So if you want to get the resultant to this, it's going to carry sine instead of cosine. So we already know the angle again that this one makes with this axis, but I think it will be easier to get the angle it makes with this axis for this case. So the angle that this one makes with this axis is going to be 90 minus 35 minus 25. So that is going to be 90 minus 35 minus 25. So you have 30 degrees. So what you have here is 30 degrees. Alright, so it is quite straightforward now. I think it is may not be so clear enough for you, so let me redraw this diagram so that you can get it better. So this is the x-axis. We have been told that the resultant of the forces, the three forces acting at point C, okay, lies along the line BC. That means the resultant of these three forces is along this axis x prime. So we are now establishing the perpendicular to this x prime. So we are saying that the perpendicular is along this. So perpendicular to this x prime. This is the perpendicular, and we are calling it y prime. This is perpendicular to this. We called it y prime, which means this is at angle 90 degrees to this. So don't forget that this is our point C, the points we are dealing with, and this is some points B as shown in the diagram. So this is some points B. So then we have been told, or have been given that we have this tension, that's the tension along the tension on the cable AC. So I've been given AC in the diagram, so we can draw that out. So let me draw that out. So we have something like this. So this goes from points A to C. Because we are dealing with the point C, the tension at point C is going to be pointing away from point C. So this is the tension we are dealing with. This is the particular tension we are dealing with. Alright. I hope this is still not confusing you. Please ignore these things. They're not necessary. So that's why I've taken this here. Alright. So I have left the other two forces that were given. So we are given this force. Firstly, we are given the force of 50 pounds. So the 50-pound force is vertically downwards. So just draw it vertically downwards. This is the way it is. 50 pound vertically downward. And we're now given 75 pounds at 25 degrees to this. So we have something like this, 75 pounds. This one is 75 pounds. So we have this. We're trying to make it quite longer, or a bit longer than this, because to reflect the magnitude, but something does make sense with the magnitude we are given. So this is 25 degrees. Alright. So from the diagram, if you extend this downwards from the diagram, you have something like this. So this is the vertical line, and the diagram says that this angle is 35 degrees and this angle is 65 degrees. Alright. So these are the three forces. I have this force T, this force 50 pounds, and this force 75 pounds. And I have been told that their resultant is along this direction, and this is the perpendicular to the direction. So it's that I will now get the tension T, that's the magnitude of this T, and then the resultant we are talking about, which we have been told is along this direction. So, and to do that, I said you will resolve the three forces along this direction. When you resolve them along this direction, those components, when you add all of them, they are going to give you the resultant of the three forces. And then when you resolve those forces again, each of these forces, when you resolve them along the perpendicular direction, the summation of those components must be 0, because that is when the resultant will only be in this direction. If the component along this direction is not 0, then the resultant cannot be in this direction. Like I illustrated, if you have some forces in this plane, you have this. Okay, if you get the resultant, can you remember how to get the resultant of the forces? You said to get the resultant of the forces, the resultant is equal to Rxi plus Ryj. So Rx is the summation of all the x components of the forces in the system. Ry is the summation of all y components of the forces in the system. So if it now happens that they are telling us that this resultant is along the x-axis, if the resultant is along the x-axis, purely along the x-axis, that means the resultant has no y components. If the resultant has no y components, that means the summation of the y components of the component forces, the forces that make up the whole system, or the forces involved in the whole system, must be 0. So that is the idea here. We are being told that the resultant, so basically you expect the resultant here to be equal to the summation of all forces along the x direction, okay, plus the summation of all forces along the y prime direction. So this is basically what is going to give us the resultant. So this is the vector equation that will give us the resultant. But now we are being told that this resultant is strictly along the x prime axis, which means that these components along the y axis for the resultant is 0. And how do we get this for the resultant? Normally, this for the resultant is going to be these components, the summation of these components for each of the forces involved. So that summation is 0. So that's what we can deduce from all of this. So that's what we want to use to get this result now. Okay, so to do that, we get the angles involved like we have done right here. This is 65, 65. These three lines make a triangle. 65, 35. When you add them, that's going to give you 100, and this will so give you 80 degrees. Alright, so you can leave it at that if you like, and then we know that this one is vertical, just like this line is vertical as given in the diagram. So because of that, we will have this angle to be 35 degrees. Okay, alternate angles at 35 degrees, just like what we have here, 35 degrees. Okay, you can go further to simplify it like this. You can get your answer directly this way. So what's our what's the first thing we want to do? We want to get T, that's the tension in the cable. So to do that, we get the components of each one of them along the y prime axis and sum everything together. When we sum everything, we equate it to 0. Why are we doing that? Because we have been told that the resultant is along this direction, meaning that the y component or the y prime component of everything sum to 0. Okay, so for T, for the first T, its component along this y prime axis. Now I'm taking this direction as positive. Okay, let us take this direction as positive. So we now say that summation of forces in the y prime direction, taking this as positive, we are taking this side as positive, must be equal to 0 based on the information supplied to us. So this implies that, so along the y-axis I have T, so I know that T makes angle of 80 degrees to x prime axis. So if I want to get its components, it's directed this way, so its component along this is going to be facing the negative y direction, okay, from what we have learned in the past. So and that component is going to be given by T sine 80 degrees. or t cos 10 degree if you were to use this angle. Alright, so whichever one you use is the same thing, and it's going to be negative because it is facing backwards. This is the first t, okay, directed away from the point C. This is point C. Alright, so because of that, I'm going to have minus t sine 80 degrees. Okay, so put that there. Then I move on to the other forces, plus I have this 50 pound force is making angle of 35 degrees with my x prime axis. Its y component is going to be directed this way, and it's going to be positive, obviously, so that is going to carry sine also. So I'm going to have 50 sine 35 degrees. Then I'm going to have plus the next one. So this angle altogether, when you add these two, you know the angle that this makes with the x-axis. That's 35 plus 25, so that's going to be 60 degrees. Or you say it makes 30 degrees with this, anyone you want to use. So that's going to be 75 sine 60, because I'm using the angle to mix with this. Or you say cos 30, it's still the same. So it's going to be positive because it's going to be facing this side. So I have plus 75 sine 60 degrees. So that is everything for the components along the y-axis. So everything here must be 0. That is when their resultants can only be in this direction, will be in this direction only. Alright, so based on this, I have now an equation that has or that contains only t as the unknown. So I can solve this equation to obtain t. So from here, what will you get as t? Now when you move 50, you can solve further, you can expand further, work on another line before you get to this. I'm trying to manage the space, that's why I'm doing it this way, so you can do that right now for yourself. Okay, so when you move this to the other side, it's going to become plus t sine 80 degrees. So what you have here is going to be just 50 sine. So ensure your calculator is in degrees, so we have to change this to degrees. So this is in degrees now. So I'm going to have 50 sine 35 plus 75 sine 60 is equal to, so that's what I will have on one side, where I will have t sine 80 degrees on the other side. So I'm going to divide this by sine 80. So sine 80, everything divided by sine 80 is 95.07. So let us see, that is 95.1 Newton, in line with our rule. Alright, so that is that about that. That is the answer to the first part of the problem. And the second part says we should find the corresponding magnitude of the resultant. So quite straightforward. I want to get the magnitude of the resultant. So you know how to get the magnitude of the resultant now. Because the resultant is along the x-axis, we know that R is equal to summation of forces is equal to the summation of forces along the x prime axis. So you can quickly do that. So we expect that everything should face here. So we can adopt this as our as our positive x prime direction. But where it faces is actually not the problem now. The question says we should find the corresponding magnitude of the resultant. So that is the magnitude. Alright, so going further, we are going to have something like that, and then so this is going to be, for this to be along this direction, to be positive, t for t to be in this direction, to be positive. Even for everything, it will be in this direction, positive. So let's just take this as a positive direction. So for this, I'm going to have t cos 80 degrees. I already know t, so I'm going to have this as 95.1 cos 80 degrees, then plus this 50 is having angle 35 degrees to that side. Don't forget, don't mix them up. This is the angle this refers to, this is the angle for this. Okay, so I'm going to have plus 50 cos 35 degrees, then plus 75 cos 60 degrees. So that's everything there. So that's going to give me the magnitude of the resultant. So when I add everything, 95.1 cos 80, 95.1 cos 80, sorry, so that everything out once. 95.1 cos 80 plus 50 cos 35 plus 75 cos 60. So that will give us our answer 94.97. So that's just 95.0 Newton. So that is that about that. So that's the answer. That's the way to deal with questions like this. So you can think of other ways to do it. If you want to do it another way, how else can you do it? You can, that's going to be quite long. I think this is the best way to do it. It's going to be long. If you want to use graphical method, I mean, if you want to use the parallelogram rule, you have to combine two at a time, so to take some time to come up with solution of that, but I think you understand this, so we're good to go. Alright. I think you should be able to solve other problems in this exercise. If it happens that you have attempted all that's in the exercises I've given you so far, 2.21 to 2.42, and you have issues with them, please let me know so that maybe I can explain some to you on the group. There will be no other class again besides this. So that's that about that. So let us look at the equilibrium of a particle. So equilibrium of a particle. So that means equilibrium. When you talk about equilibrium, you're talking about the body being at rest or being under uniform motion, and in motion with constant velocity. Alright, so that means motion with zero acceleration. When the acceleration is zero, that means the velocity is not changed. The velocity can remain at zero, it can remain at some constant value. So it can be at the velocity is zero. If the velocity is zero, you have the body to be at rest. If the velocity is non-zero, that means the body is moving with constant velocity and it's under uniform motion, as we like to call it. Okay, so what condition will a body be in equilibrium? Generally, when you use a body, you know by now from what we have learned so far that you should be specific. Are you talking about a particle or a rigid body? So in this case, we are dealing with a particle. So in under equilibrium of a particle, we are now dealing with a particle. That means a single point body, or a body that can be assumed, or a body on which forces, or a station on which forces acting on the body can be assumed to act at a single point, okay, without appreciable error. So that's what we're dealing with here. So equilibrium means that we have a particle or a single point at rest or in uniform motion, and that can only happen when the resultant forces on the body is zero. Okay, so that is the idea we have seen from Newton's first law of motion. Okay, so that's exactly what we are doing right here. So for the equilibrium of a particle, it is sufficient, or it suffices, to have this condition that the summation of forces on the body is zero. So if the summation of forces on that body is zero, then the particle is in equilibrium. Why don't you bother about the moment of the forces? It is because we are dealing with a single point body, and because it's a single point, there is no possibility of rotation about the point, or for you to have rotation about a point, you must have at least 2 points, such that one point is rotating about the other. In this case, we have just 1 point, so the discussion of rotation about a point does not come into play. So this is a necessary and sufficient condition for the equilibrium of a particle. Alright, so we can break this down into scalar forms of summation of forces in the x direction being 0, summation of forces in the y direction means 0. And if we're dealing with a 3D situation, to also follow that summation of forces in the z direction is 0. So these three, okay, are necessary and sufficient for the equilibrium of a particle in 3D. So, but for now we are dealing with 2D. We have not commenced the 3D stuff yet, so it's okay to just deal with these two, that for the equilibrium of a particle in 2 dimensions, summation of forces in the x direction is 0, summation of forces in the y direction is 0. Alright, so these are the conditions right there. And then, so what is this going to mean? If we have summation of forces to be 0, that means, you know, from what we have done so far, if you have what is it now? If you have just 2 forces acting on the particle, for instance, this is a particle. If you have just 2 forces acting on it, let's say you have a particular force acting this way. Okay, for this particle to be at equilibrium, obviously you must have another force oppositely directed, which is equal and opposite it, so that this particle will be at equilibrium. Quite straightforward when you have just one force. When you have just 2 forces acting on the body and the body is on equilibrium, they have to be equal and oppositely directed forces, okay, acting on that particle. Alright, now if you have 3 forces, what is going to happen? If you have 3 forces acting on the body, this, and the body is in equilibrium, what is the implication? It happens that, of course, their summation is 0. That means when you sum the 3, you're going to have 0. And what is the implication of that? You know, this means that your F1, F2, and F3, when summed, will give you 0. And we can remember from our parallelogram rule, parallelogram law of vector of forces, parallelogram law of vector addition. Okay, we remember that if we are to sum this, you know, for equilibrium now, we are going to have summation of F is equal to 0, which means that our F1 plus F2 plus F3 must be 0. So this means if I position my F1, let us see, I start this way, I position my F1, this is the force F1, I position my force F2, I want to add them, so I want to add them, I have to proceed in tip to tail fashion. So I'm going to put this, the tip of this at the tail of the other, the tail of this at the tip of this now. Alright, so this is F2, I'm going to pull it, put the tail at the tip of this. So I'm going to maintain the orientation like we did in the past. So I'm going to do something like this. This is what I have right here. This is the force. So we are saying that everything, when I sum them, it must give me 0. That means when I add this to this, how do I add this to this now? I position again the tail of this at the tip of this. So I'm going to have something like this. So it must be something that gives me 0. Giving me 0 means that it must return, I must return to the starting points if I sum all of them. So far this body is in equilibrium. So I'm going to have this. So I'm going to have a triangle at the end of the day, so I can easily use this triangle of forces to solve problems, okay, when I have, you know, a particle in equilibrium because of this condition. So it must be that when I arrange all of them in a tip to tail fashion, it must give me a closed figure at the end of the day. It's not that I'm trying to close it, okay, this one will naturally give me a closed figure at the end of the day if the body in consideration is in equilibrium, is to be in equilibrium. Alright, so that is the idea right here. So it may happen that this will come handy if you are dealing with just 3 forces being responsible for the equilibrium of the body. If it happens that there are more than 3 forces being responsible, that means you will have to break them down into x components and y components. X component and y component do not necessarily mean vertical and horizontal component. I think I've said this, I've stressed this quite a number of times now. X component and Y component simply means you have two perpendicular components. So that is what it is. They may not be vertical and horizontal. For instance, like the one we just did right here, you can see our X and Y were not vertical and horizontal. We just had to use, two convenient perpendicular directions. So that's what this implies. Whenever you see it, it's just that should be the thing to come to your mind. You are using two convenient perpendicular directions. Okay, so that is that about that. So if it happens that you have more than 3 forces, you're going to get summation of the forces in the x direction equated to 0, equation 1. Summation of forces in the y direction equated to 0, equation 2, which tells you that when you have a problem having to do with equilibrium of a particle in 2 dimensions, you can only solve for 2 unknowns. You cannot solve for more than 2 unknowns, because when you have more than 2 unknowns, of course, that is already becoming an indeterminate problem. You cannot solve that using the rules we have learned here. Okay, you will not come across that anyways as far as this topic, this section is concerned. Okay, so if it happens that there are just 3, you know what to do already. Use your triangle rule. It just happens that is the fastest way to approach it. When you have just three forces, this is the best way to approach it. It wastes time to begin to resolve them into components when you have just 3. And if you have more than 3, it's going to give you some complex polygon. Complex is relative. You may find it easier to do. Maybe you can do that comfortably. You are okay with that, it's fine, you can proceed. But it is just the best thing for you, the fastest thing for you to resolve into x component and equate to 0, you resolve into y component and equate to 0. So that is that about that. So let us solve one problem on this before we end this class. So let's pick this example. Let's do this as example 2.46. 2 cables are tied together at C and are loaded as shown. Determine the tension A in cable AC and the tension in cable BC. So you can see some things right there. You can notice something. You will notice that there are just 2 unknowns. We want to get the tension in cable, where is it now? AC. So this tension in cable, this is the cable AC. We want to get the tension in this cable. Then we want to get the tension in cable BC. So the tension in this cable is just going to be equal to the weight of this load right here, 200 kilograms. So you get it in weight form. I've told you are going to use G equals 9.81 all through in this course. Don't forget that, unless otherwise expressly stated in your question. You use another value of G. Your G is always 9.81 meters per second square. So we're going to use that to convert this to weight and to have this in Newton. So with that, we will get the tension in cable AC and the tension in cable BC. So what kind of question do you think this is? In this case, it's quite not obvious, but you should notice that this point C is the common point. So it's as though the tensions being referred to here all emanate from, of course, it is not as though, it is actually that all tensions being referred to here emanate from the point C. So what we are dealing with is equilibrium. This is a question that has to do with equilibrium of the point C. So we want to analyze the point C for equilibrium. So the first thing to do is to produce a free body diagram. A free body diagram of the point C. That means we locate the point C, then we also put in the different forces. Don't forget these are going to be tension forces, and as we have severally said, tension will be directed away from the point in consideration. So the tension at point C due to the portion BC of the cable is going to be directed from C towards B. So the tension in the cable AC, okay, at the point C is going to be directed from the point C to the point A in that direction. In the same vein, this weight, the tension due to this weight hanging on this portion of the cable is going to be directed vertically downwards, as it's expected for weight. Whenever you come across weight, the direction is going to be vertically downwards. So that's what we put there also. Alright, so we know from this diagram, we know the direction of all the forces involved. We can see that this one is at 75 degrees to the horizontal, this one is at 75 degrees to the vertical, whereas this is vertically downwards. It's a weight. So with that, we are good to go. We have three forces. We draw the free body diagram, and from the free body diagram we produce our triangle, our first triangle, and from the first triangle we get the unknowns involved. Alright, so that's what we want to do now. We start with the free body diagram. Okay, so the point C. This is the point C. So the weights due to the 200 kilogram load is going to produce a tension vertically downwards, and this tension is going to be given by 200 kilogram multiplied by 9.81 meters per second square. Alright, so that is going to give us, let's put it directly, 200 times 9.81, so we have 1962. So we have 1962 Newton. Alright, so that's sorted. Then we have the force from the point C to the point B. We're told that it's at 75 degrees to the horizontal, which means that 15 degrees to the vertical. So we have something like this, as given in the diagram. This free body diagram is important. I cannot overemphasize that. So this free body diagram is important. This free body diagram is important. Free body diagram is always important. Please place. So we're given that this is at some angle 45 degrees to the 75 degrees to the horizontal. So if you like, you can leave it that way. If you like, you can say that this means it's at an angle 75 degrees this way, or you say 15 degrees this way, anyhow you like it. Okay, then the next one, you don't mind my rough diagram. Okay, just what's important is, do you understand the directions being indicated, the magnitudes, the way they are being indicated? Okay, that's what we want to see. It's not fine arts. Okay, so forgive me if it's not fine. Alright, so then we have these from here to here, and then we are told this is at 75 degrees to the vertical. So we have this downwards 75 degrees. So if you like, you can say to the horizontal this way, or this is vertical, so you can say this is 75 degrees, you can say this is 15 degrees, anyhow you like it. So that is about that. So they said this is tension in cable. Of course, this is tension in cable BC, so I can put this as T subscript BC. This tension in cable AC, you can put this as T subscript AC. So I'm done with the free body diagram. That we have extracted all the information we need from the given problem statement. Okay, so we'll now proceed to say, okay, the method we want to use is a triangle method. So because of that, we write that for equilibrium of the point C, summation of forces acting at the point C, okay, must be equal to 0. Okay, so because of that, it is because of this that we can now put together a force triangle, okay, that depicts the formation, the summation of forces being 0. So we're going to do that right now. We arrange them in tip to tail fashion, don't forget, until we get a close figure. Okay, so we have this one vertically downward, so we can just put that vertically downward. Why am I using dotted lines? You get to see. Then we have this this one is vertically downward, so open for something like this. And then we have this one going this way. Don't forget, we want to arrange them in tip to tail fashion. So if you want to put this next, you should move this tail to the tip here, or if you like, you want to put this next, move this tail to the tip here. So anyone you want to do or you would like to do. So let us say we want to move this right here to the tip here. So I'm going to have something like this. From here I'm going to have this, such that this is at 75 degrees to the vertical. So this is at 75 degrees. Then I'm going to add this again from the tip of this. So from the tip of this, I'm going to have something like this. So I have that right here. Okay, such that this is at angle 15 degrees to the vertical. So what I have here is 15 degrees. It is 75, which means, of course, now I can use this. I can use thick lines for this because I've gotten a close figure already. So this is going to be my 1962 Newton. This is going to be my TBC, obviously, and this is my TAC, as you can see. Alright, so now I've concluded that when you sum this, you go this way TAC, go this way plus TBC, come this way plus 1962 Newton and downward. Everything is zero because you return to the starting point. So that's the meaning of all this. Alright, then we need to get the angles. So we go this way. This is a straight line. Angle on the straight line is 180 degrees. So this is going to be 180 degrees minus 75 degrees. I think that is 105 degrees. Let's be 100% sure. 180 minus 75, 105. Okay, so then we also get this angle. This is 15 degrees. This is 105 degrees. When I sum everything and subtract from 180, I should get this angle because some of the interior angles of a triangle is 180 degrees. So this is 105 plus 15, so minus 180. So I'm going to have 180 minus answer 60 degrees. So this is 60 degrees. So now I'm good to go. So this represents the three sides of a triangle. So with this, I can get whatever I need to get using any of the rules of solving sides of triangles that I'm familiar with, whether a triangle, whether the sine rule or cosine rule, anyone that is convenient or appropriate, or will give us the fastest results here. Alright, so now we want to get firstly the tension in cable AC. So we want to get TAC. So which of them will give us TAC faster? We know all the angles, we know one of the sides, so we can use sine rule. So I know that TAC divided by the sine of the angle opposite it, that's TAC divided by sine 15 degrees is equal to TAC divided by sine 15 degrees is equal to 1962 divided by the angle opposite it, sine 60 degrees. Alright, so from here I get my TAC to be equal to 1962 sine 15 degrees divided by sine 60 degrees. Okay, sine 60 degrees. Alright, so this is going to give me TAC. So I have TAC equals 1962. So I have 1962 sine 15, 1962 sine 15 divided by sine 60. So that's 586.36. So in line with our convention, that's just 586. So I have this to be 586 Newton. So that's all about that. And I go for TBC. So TBC is equal to, this is going to be TBC by sine rule again. TBC over what's the sine, or what's the angle opposite it? 105 sine 105 degrees is equal to this TBC over sine 105 is equal to 1962. I'm still using 1962. I don't want to use this one because I've done some approximation. It may not be significant when you put it, but the approximation error may affect this. It may not be significant anyways, but it's good to just use this because no approximation has been done so far. So 1962 over sine 60 degrees. So from here I'm going to have my TBC to be equal to 1962 sine 105 degrees divided by sine 60 degrees. So from here, I'm going to get my TBC to be equal to, so I have 1962 right here. Instead of 15, I have 105. So this is 2188. So how do we put that? It's already in 4 significant figures, so I can put this as 2.19 kilonewton. So that is that about that. Right, so we got our answers. So I think that is the end of today's class, and that is the end of live classes for now. I don't know. I'm hoping that the school will resume next month, June. So when school resumes proper, we're going to have proper classes and do these things together live. So we're going to begin by the time school resumes with forces in space. Although we have done it before, but I think that is where the technicality begins, and it's just good that we take our time to understand that aspect properly, and the lecturers haven't got there, but that's not really the issue. The issue is that it will take lecturers just one class or two classes to cover this chapter, so it's not something we really have to wait for lecturers over, but it's just good that we do them when we are physically present. But if it happens that restrictions or guidelines given by the school or to be given by the school would not allow physical classes to hold, or would not be favorable for continuation of physical classes, then we will have to continue online, but that would mean we'll have to use a different facility so that you can relate with it better. Alright, so but that is all for now. Thank you for your interest in Maths Engineering tutorials.